look at y'all. They are all set up. Okay. Hi, Ryan. We can't hear you if you're talking. Keyshawn, can you hear them? Is it me?
Ryan, could you say something real quick?
Hello.
Okay, yeah, we can
There
hear
we
you.
go. Excellent. How are you?
Good.
It's been so long.
I haven't seen you since I went to Atlanta.
Right. Since Space Day. It's been some time. I hear you have a book.
Uh-huh.
You wrote a book. I'm so proud of you. Congratulations.
Thank you.
You're so welcome. And hi, Mom.
Hi, how are you?
Doing well. Thank you so much for joining us today.
No problem.
Excellent. I think we are waiting on 3 more, so we'll give them some time. Let's see. Oh, also, Keyshawn, I have on the automatic captioning. It looks like it's doing a good job.
It looks good to me, yeah.
Okay, sweet. Oh, I know we didn't have Vidman Barber for this, just in case people need it.
Right.
Mhm. Oh, there we go. There's Kai. Thanks for time. Okay. All right, we got Kai in here.
Hi, can you hear me?
Did you say Naia?
I'm talking to Kai. Kai, do you hear me?
Oh,
Yeah.
Okay. Hey, Kai.
hi Kai. Nice to meet you.
Hi,
Thank you for joining us. All right, we got one more waiting on. Let me check with Ash. Oh, and there she is.
There we go.
Hi, Jovita, Jade, and Journey. Hi. Excellent. So we got everybody here. When everybody's settled, just give me a thumbs up, either virtually or with your actual thumbs, and we'll get started.
Bye.
Okay, thank you, Rye. I see your thumb.
Welcome.
I like your baby doll. What's her name?
McKenna.
McKenna. That's a beautiful
Uh-huh.
name.
I actually took her when I went to Atlanta.
Oh, you did. That's right. I remember that. Thank you, Kai. I got your thumbs up.
Hey, Keenan. Was that Keenan? Hey.
What's up? What's up? What's up?
Okay, we got our third thumbs up. Excellent. Well, welcome to the CubeSat workshop for Black Space Week 2024. We are super, super excited to have you and super excited to do this experiment. We'll get to experiment soon one day, hopefully. But this exercise with you, we're going to be building some mini satellites. So I'm going to go ahead and start my presentation, which I should get through quickly. I don't intend to bore you. But please be prepared to interact back with me. This is not a lecture. We're going to talk to each other and have fun. Hopefully. Well, hopefully you have fun. I know I will. Oh, I'm sorry. Keyshawn, I just got a message from Cadence. Do you mind getting her the Zoom link?
I will send it her way. Yep.
Thank you so much. Let me know if you need her updated email. Okay, moving on. So I will first start by introducing myself. My name is Naia Butler-Craig. I am the aerospace chair of Black and Astro. And Black and Astro is also, if you are not familiar yet, Black and Astro is an organization that seeks to amplify the voices, create community for, and provide opportunities for Black students in various space fields. So there's aerospace, there's astrophysics, and everything in between, space law, space policy, all those good things, because we understand that we provide so much value and have so much talent within our communities, but don't always have the resources that we need. So Black and Astro is a really, really great organization. Black Space Week is our flagship event that we do every year. And we're really excited to extend our programming through the K through 12 pipeline because you all, Jovita, Ryan, Kai, I'm sorry, not Jovita, you too, Jovita, but Jade and Journey, Ryan, Kai, you are the future of the space industry should you decide to pursue space careers. So we really want to engage you, get you some experience with what we do so that you know what to expect and you continue to learn. So a little bit more about me. I'm an aerospace engineering PhD candidate at Georgia Tech. I focus on building and testing electric rockets. Now, I would like for each of you to introduce yourselves, and I did forget my little bullet points, so ignore that little blurb there. But let's start by introducing your name, where you're from, your age, and what you like most about space. And I will call you out. Let's see who I'm going to start first. Let's go with Ryan, because I just know you're ready.
My name is Ryan. I'm 8 years old.
Where are you from?
I'm from Philadelphia, Pennsylvania. And then what I like about space is all the different planets and continents.
Excellent job, Ryan. Thank you so much.
You're
Let's
welcome.
go down. Oh, you were so sweet. Let's go down to Kai.
I'm Kai. I'm 12 years old. I'm from Texas, and what I like about space is all the different continents.
Okay, very nice. So constellations, you like the stars and how they interact and how I love it. I love it. How they make pictures and figures. I'm not the physicist of our group, so I'm gonna let Keyshawn chime in about what constellations are. But those are actually really cool. My favorite is Orion's belt. If you look it up, it's just 3 stars in a row, and I actually got that tattooed. Don't get tattoos, but just to let you know how much of a space nerd I am. I like those too. So let's go to Jade first, because I think I can see Jade.
So
Or is that Journey?
That's Jade. Me.
Speak up, she can't hear you.
Jade.
Go ahead.
So my name is Jade. I'm 7 years old, and I'm from Ellenwood, Georgia. And then my most favorite thing from space is that there's no gravity in space.
I love that. Miss Journey?
Oh, she left.
Okay, it's okay. Sounds good. I like that there's no gravity either. When you get on the scale, you don't have to worry about not liking the number that comes up. So you guys don't have to worry about that, but people my age do. Okay, just got your message. I'm gonna check in with Cadence in a moment. Keyshawn. Okay, so let's move on to what is a CubeSat. Does anybody know? Has anybody ever heard of CubeSats before? Let's get some wild guesses. Anybody want to take a stab at it? Let's go, Ryan.
Is it like a box that goes into space?
Absolutely. That's definitely one way to talk about it. Yes, and that's a really good. Is that a guess or did you know that?
I kind of knew I kind of did and I kind of didn't.
I like it. I like it. That's really, really good. That's exactly what it is. Any other guesses? Anybody want to take a stab at defining what a CubeSat is?
I would.
Okay, yes, Miss Jade.
It's a cube shaped satellite.
Good job. That's exactly what it is. And it looks very much like a box, which is also a cube. So you and Ryan are both on the money. So anybody have any ideas of what they're used for? Okay, Ryan.
Is it used to send stuff to Is it used to send stuff into space to transport stuff up in space?
Yes, ma'am. That's exactly right. That's definitely one application. And that was also a trick question. Can anybody guess why that's a trick question? Okay, no worries, because you will learn in a minute that CubeSats are so versatile, meaning that they are very, I don't want to say flexible, but they can be used for a variety of missions. And that's why they're so valuable. So if you were to say one thing, Ryan, and Kai were to say another, say, Ryan, you said, I want to explore the moon's atmosphere. Well, the moon doesn't have an atmosphere. If you want to explore another planetary atmosphere, say Jupiter, you could use a CubeSat for that. But say Kai says, well, I want to actually look at our Earth and our oceans from space. You could also use it for that. So you could use it for various things, whether it's looking or having to do with our planet Earth, or even interplanetary missions, meaning that you use them for different planets. So what are some planets, Ryan? Name some of your favorite planets.
The Earth, the Moon.
Love it.
I like Uranus,
Nice.
Saturn, because I like
Okay.
its rings.
Very nice. Me too. It's very, very aesthetic. It's a very pretty, pretty planet. What about you, Jade? What are your favorite planets?
Jupiter, Saturn, and Mars.
Very nice. And what about you, Kai?
Jupiter, Saturn, and Uranus.
Very nice. Okay, so keep your favorite planets in mind, because I'm going to come back to that. So to go into, I mean, you perfectly defined it already, but I will reiterate. A CubeSat is a tiny satellite, and it's shaped like a cube, and it's used to do experiments and take pictures in space. Has anybody, well, it's on the screen, but does anybody know how CubeSats are launched? You can just read the screen if you want to. Let's hear from Kai. I want to hear more from you.
They're launched as secondary payloads during rocket launches or even from the International Space Station, a research lab in space.
Yes. Have you all heard of the International Space Station, the ISS? Raise your hand if you have. All right, Ryan, Kai. Jade, have you heard of the ISS before?
No, I haven't.
I love it. Okay. Well, the ISS, the International Space Station, is a research lab that orbits Earth. So it's in space, and we send astronauts up there to do research, all kinds of research, but different research missions. And what's really cool is that there are some people who will have their CubeSat launched to the International Space Station or with the astronaut. And guess how the CubeSat gets into orbit? Can anybody guess? Yes, Ryan?
Does it work in space by using the space's gravity?
They can do that too. That's definitely that. So that's what so when they go into the orbit, they're definitely using planetary gravity, whether it's Earth or another planet. But guess how they get there? I'm just going to say it because I think it's the coolest thing ever. You can have an astronaut throw your CubeSat into its orbit. Can you imagine that? An astronaut being on the space station, which is the orbiting space lab. They have your CubeSat that you're going to build today, and they just toss it out and they deploy it from the space station. Who would want that? I was gonna say, am I the only one that think that's so super cool?
That's hilarious.
I said the same thing. I couldn't even like visualize that. I'm like, are they just tossing it? But yes, that's a possibility, and people have done that before. And it's something that I want to do when I become an astronaut. So, a little bit about CubeSat history. They were first made by students actually in 1999 at California Polytechnic Institute. And before 2014, they were mostly, or most CubeSat launches were by students in colleges. And then after that, because they are so small and compact, they've been able to be used by various people, whether you're in the space industry as a professional or you're even in middle school. So people as young as you all actually have built CubeSats and launched them through various initiatives. So this is what I love so much about them, is because anybody can do them. And NASA has a very, very interesting initiative where they send up CubeSats made by people just like you and me. And I think as young as elementary school, I've heard most recently they've had a mission, but definitely middle schoolers and high schoolers and definitely colleges. And so after you build your model one, there's fully a possibility that when you get to high school or when you get to college, you can have one of these, or you can be part of building and launching one of these yourself. And this is me actually on the right. This is me building a CubeSat that was launched in 2018. And this was a very long time ago. But as you can see, you see how tiny this is? Can you guys see my cursor? I don't know if you can, but do you see that metal frame that's in this picture with me? Can you guys guess how long that is? It's okay if you can't. Does anybody have a loaf of bread on them? It's okay. I have my own. I'll grab it. So that CubeSat I'm building in that picture is this long. It's exactly as long as a loaf of bread. And what's really cool about that is, remember, CubeSats are tiny satellites. So satellites used to weigh 1 ton. They're huge. They're probably as big as, they could be as big as the room I'm in right now, or as big as the rooms that you're in right now. But they were able to condense all of the things happening in a huge 1 ton satellite into something that you can find in your kitchen, into the size of something that you can find in your kitchen. And so what you're going to build today is something called a 1U CubeSat. So Miss Ryan, you said it perfectly. It's a cube, it's a box, right? That's considered a 1U CubeSat. If you have 2 boxes and you stack them on top of each other, that's a 2U. If you have 3 boxes and stack them on top of each other, what is it called? I can't hear you, Ryan.
A 3U?
Exactly. So in this picture, that is a 3U CubeSat. So I'm gonna play this video. You guys, you ladies, let me know if you can hear it.
I can't hear it.
Can't hear it? No problem. Can everyone else hear it?
No, I can't hear it either.
Okay,
I can.
I'm sorry. Oh, interesting. Okay, let's see. Let's see if this works now.
What is a CubeSat? CubeSats are very small spacecraft that orbit Earth. As you might guess, a CubeSat is shaped like a cube, about 4 inches wide, long, and deep. That's called 1 unit, or 1U, small enough to hold in your hand and very light, around 3 pounds. And like building blocks, units can be combined to make bigger CubeSats by stacking them into 2, 3, or even 6 units. Once in space, CubeSats can open up all kinds of tools.
Oops, I'm sorry.
Solar panels for power,
Oh,
communications antennas, telescopes, and more. CubeSats are great because they let schools, universities, and other teams launch their very own missions, and who knows what they'll
I'm sorry. I'm trying to make sure Cadence gets this link.
CubeSats are also made from standard, low-cost parts that are
Oh my
easy to
gosh.
get and tested for launch safety. Some NASA launches carry spacecraft that don't take up all the space on their rockets, which leaves plenty of room for tiny CubeSats. Build a CubeSat, catch a rocket ride, and you become a space explorer.
Okay. I'm sorry for all the pauses. I can replay that if needed. Did all that make sense? Excellent. Okay, so there was one thing he said in there, and I did pause it during this, so I can replay it, but this is a bit of a quiz. Did anybody hear what components make up a CubeSat? The things he listed off? Anybody remember even one of them? It's okay. I'm a nice teacher, so I'm gonna run it back just a little bit.
Can open up all kinds of tools: solar panels for power, communications antennas, telescopes, and more. CubeSats are great because they let schools, universities, and other teams launch their very own missions, and who knows what they'll discover. CubeSats are also made from standard, low-cost parts that are easy to get and tested for launch safety. Some NASA launches carry spacecraft that don't take up all the space on their rockets, which leaves plenty of room for tiny CubeSats. Build a Cube.
I'm gonna pause it there. Did anybody hear it that time?
Solar panels.
Good job. Ryan, did you have one?
It's carried by rocket.
Exactly. And so that's why they're so cool, because the things that you put on a CubeSat, you can find and buy. They call it commercial off the shelf. It's something called COTS, C-O-T-S. That's an acronym NASA uses. But that just means it's almost like if there was a Walmart for CubeSats, you could buy them there. They have a version of Walmart for CubeSats where you can just buy those things and put them in your CubeSat and launch them. And that's why they're so easy and accessible. So that's why they're important, because everybody likes cheap stuff.
CubeSat.
Likes to do things
Catch a rocket.
cheaply. And so somebody already said, what do they include? Electrical power system, a command and data handling system, communication system, and payload. Now I'm going to take you to your kits. Can everybody bring their kits or show them to me? So I make sure you have the right pages. Let's see. I want to see the back.
You want to the back? Lift this up like a book.
Oh,
She's so cute. Perfect. Okay. So does everybody see where the CubeSat components are? So it should say command and data handling. It should say all the things on the screen, but electrical power system. And everybody see that? Okay, Kai, see you nodding. Ryan, you see it. Jay, do you see yours?
yes.
Excellent. Okay, so these are all of the CubeSat components, or you can, another word for them is something called subsystems. And so that's what we're going to be working with today. And we'll get to this, but essentially this is what we're going to build, and it has all the same things we just talked about. And we'll go over what each one of those means. And we're going to start building now. So we got our CubeSat components. I'm going to call on Kai. Tell me what a command and data handling module does.
Oh, okay. The command and data handling system is the brain of the whole anonymous CubeSat. The CNDH system consists of an onboard computer, OBC, which controls the operation of the CubeSat while in space. The OBC houses the flight software that will manage the various tasks that the CubeSat performs on orbit.
Great job, great job. So your CubeSat is like a system, and what did I call these again? Everybody remember the second word I used for these components?
You remember that? We all said it.
No, I
subsystems. Right. So your CubeSat is your system. These are your subsystems. And I like to think of a system, your body is a system too. So your brain, your eyes, your arms, your legs, your feet, they're all subsystems. So the command and data handling component or subsystem of the CubeSat is its brain. So Ryan, can we now move on to describing what the electrical power system is?
The electrical power system wraps the CubeSat. The electric power system.
The electrical power system of a CubeSat provides electrical energy
and
to
do all the am in
The system
the
board.
board and it is most critical system of satellite.
Excellent job. Excellent. Good job, Ryan. So okay, so I said that the command and data handling system is the brain. Electrical power, it powers the whole system. That's how it basically comes alive. What do you guys think? Or actually, I'll just say it. I would refer to electrical power system in our human body system as like the food we eat. That's kind of how we're powered, right? So that's what its purpose is. So whatever's on there will need electrical power to turn on to work and to do the science that we want to do. Let's move down to the communication system. Jade, will you do the honors of telling us what a communication system is?
The communication system allows the satellite to communicate with ground stations on Earth to pass along data from the CubeSat. The communication system using a selected frequency consists of the CubeSat radio transmitter and receiver antennas and an Earth ground station.
Exactly. Great job. And so that's how we actually get the data that we're taking up in space when we launch our CubeSat. That's how we get it back down to Earth so we can actually know what we're doing. What's the point if we can't get the data back, you know? So that's what that's for. And then the last thing is a payload. Also, Keyshawn, it looks like Kate is on, but she is a participant.
I'll move her.
Is there any way?
Yeah, I can.
Okay, thank you.
Yeah.
You're the best. Okay, so I will do the honors unless somebody wants to talk about the payload. Any
I'll do it.
takers? Oh, yay. Okay, go ahead, Kai. What is the payload?
Okay. The payload can include instruments, sensors, or science research designed to collect data during orbit. The payload is interfaced with all the system of the CubeSat to ensure it has power and software and communicate with the Earth's ground station.
Excellent job. So the payload is basically, I would call that mission specific. So let's see. Ryan, you said your favorite planet, one of your favorite planets was Saturn, right? What do you want to learn about Saturn that you could, well, let's just say, what do you want to learn about Saturn? Anything.
What planet you want?
I about the things in it.
Jupiter.
One more time, City. I didn't hear you.
I wanna learn about what's the different types of stuff, like different molecules in rings.
Very cool. So say you wanted to use a CubeSat for that, what you'd need are maybe some sensors or some specific equipment so you can learn about what you want to learn about Saturn's rings. That is what your payload would consist of. So let's go ahead and start our mission building activity. And while we, actually parents in the room, this is where I need you because it's a little bit hard to walk through this virtually. But does everybody see this card on there? I took mine off, but it should be, there's a perforated line. This card is your instruction sheet.
You talking about right here?
Yeah.
Yes, ma'am. So it should say it says the assembly instructions. So, the parents, I'm gonna need your help walking through those. But some other tools that you need. Uh-oh, did I miss something? Okay. Some other tools that you'll need are glue/tape. It's up to you, and some scissors. Excellent. Everybody got your tool belt?
Glue. Okay, and my favorite scissors. When your scissors small ones, I hate that shit.
And while we get situated, parents, if you don't mind starting them on steps 1 and 2, we're gonna hear some really cool, inspiring stuff about a real life aerospace engineer scientist who uses CubeSats for her own research. So Cadence, is this a good time?
It's a great time. Yes. Hi, everyone.
Excellent.
Hear me okay?
Hi.
Can you hear me? Everybody good? Cool. I'm actually sitting in my car right now. I'm sorry about that, but I'm gonna turn my camera on to wave at you briefly. So hi, it's nice to meet you. I'm Cadence. I just got my doctorate degree, so I studied for 6.5 years to learn about CubeSats and how to use them, and all the different types of ways. So I'm going to be showing you all a few ways today. If do you want me to go ahead and get into the presentation, Naia? Oh, there we go.
Sure, do you have slides?
I do, yeah. So I put together a
Okay,
couple slides with some examples. If you all are okay with me kind of going through those while you're building your thing.
yes. And parents, is that okay? Do you feel comfortable walking them through these steps at least on the first side while we listen to Dr. Payne? Okay, thank
Wonderful.
you.
Okie dokie. I'm gonna share my screen really quick, and it might be a little bit of a jump scare. Oh no, I can, okay. I can block my desktop so you don't have to see that. Yeah, so today I'm gonna show you all a few things that you can do with the CubeSats that you're building. So you have these models that you're building. And I like to tell people that they are small but mighty, because they are super tiny. I'm sure you all have talked about kind of how big they are. I'm sorry I missed the first part of your all's chat. But for me, the CubeSats that I work with, they're either the size, yes, yay, amazing, of a loaf of bread, or which is what's called a 3U, or they're around the size of a shoebox, which is called a 6U. So I am going to be telling you a few of things that you can do with either those bread loaf size or shoebox size spacecraft. So to start off, I thought of this last night because I was sitting down and I was thinking of why or the reasons why I think CubeSats are really important and the different ways that you can use them. And so I just wanted to kind of briefly talk about that before I show you some cool examples. So the first thing that you can do with them that are really cool is that you can actually dedicate them to do science. So you were mentioning, someone was mentioning that they were really interested in studying Saturn. A lot of people are really interested in studying all different types of things about the Earth, or about or about space. And so what you can do is you can take these little tiny spacecraft and you can dedicate them to studying one or multiple things from space for Earth or for other things, which is really cool. Another thing you can use these things for is technology demonstration. So I'm sure you all are familiar now with things like AI and ChatGPT. And so there's a lot of technology being developed for all different parts of life. And one thing people are usually interested in doing is demonstrating that technology in space. And so that could be one example of something that you demonstrated in space. Maybe you are taking pictures of the Earth from space and you want to use like this cool piece of technology to kind of identify the things that are in your picture. So maybe you're looking at trees or you're looking at water or any kind of object that you're interested in on the Earth from space. You can use different types of technology to see that. And if it's a new enough technology, you can actually demonstrate that for the first time in space. And CubeSats, because they're so small, tiny, and relatively cheap, are really good platforms for doing that. Another cool thing that you can use CubeSats for is to support bigger spacecraft. So I don't know if you all remember the last Mars rover that went to land on the surface of Mars, but they actually had a couple of CubeSats along with it that were called Marco. And Marco watched the whole mission happen, and it took really good data, and it was a really good support for this larger mission. And then NASA also has another mission called DART. Have you all heard of DART? Yeah? Have you heard of it? Basically, NASA was like, okay, what if we were in this situation where we saw that there was an asteroid coming towards us, and it was like kind of gonna get a little too close for comfort. Could we actually move that thing out of the way if it was coming towards us? And so what NASA did is they sent up a spacecraft and they ran it into an asteroid to see if they could actually push it out of the way. And they were able to successfully do that, which is really cool. So now we know that we can actually protect ourselves from giant rocks, which unfortunately the dinosaurs did not have an opportunity to do. So it's really cool that NASA was able to demonstrate that. And the whole act of running something into the asteroid was actually recorded by a CubeSat. So that was really cool, and it was another cool opportunity. And then the last thing is to break into space. So doing exactly what you all are doing now. You're learning about these instruments, you're learning what it takes to actually design and build a CubeSat, and you're building your own models yourselves. So it's a really cool opportunity, a really cool platform to allow folks, even, starting as young as you are, to get into space and to get excited about space. And it also helps countries around the world who maybe don't have space programs kind of get started with space a little earlier, which is very exciting. And I put a little logo down here in the corner. So this is actually from a mission called Eros. And Eros was Portugal's very first nanosatellite mission that launched earlier this year that allowed them to become more active in space. And I had the honor of helping them design that. So I'll talk a little bit about that in just a second. But now I'm going to get into some examples. So the very first mission that I'm going to talk about is actually out of my lab from grad school. So I was in the STAR lab at MIT, where I worked on 8 different nanosatellite missions, one of which was this called NODE. So NODE it's a lot of fancy words. So it's nanosatellite, which is another word for CubeSat, optical, which just means light. You're using light for the mission, and then the last 2 words, demonstration experiment, which, if you remember from my previous slide, just means that we're demonstrating some type of new technology that's never actually been used in space before. And so this was quite literally just space lasers. If you think of like something like Star Wars, where there's like lasers flying around everywhere, it's sort of kind of similar, but we were doing it for peaceful things. We just wanted to talk to the ground from space using light. So if you think about your cell phones, your radio in your car, if you're not connected to Bluetooth, all of that uses what's called radio frequency to communicate. But we use light from space to talk to the Earth. Naia? Yes.
I just think that's a perfect time to ask, does anybody know which subsystem that we just talked about relates to what she just said?
Ooh. There's a hint on the screen, right under the CubeSat model in this area.
I can't see it.
Like for
You see it?
communication payload.
Perfect. Yay!
Good job.
Amazing.
Sorry.
So yeah, no, that was great. That was great. Please feel free to interrupt and ask questions as I chat. So exactly, yeah, it was a communications payload. And again, it was a technology demonstration because nobody had ever previously communicated from space to Earth using a laser. And so we were actually able to fly that and demonstrate that a couple of years ago. And it was really exciting. One thing that I want to point out to you all, if you see this right here, can you all tell me what this is, what I'm circling with my mouse? Yeah, Ryan?
A telescope?
Yep, it's a telescope. So this is something like you would have maybe like, or you'd see at a museum, or maybe you'd have a small one in your backyard or something. So it's just a telescope. And because we're using light, you can actually use a regular schmegular telescope to receive data from space. And so on the next slide, I want to show you the difference between, if you remember, I was saying like your cell phone or your radio, they use radio frequency communication. And when you spit out radio frequency waves from space, they tend to get big really, really fast. And because they get so big so fast, you need these huge buckets on the ground to actually collect the signal from space. So if you see on the left here, my mouse is actually, this is me several years ago. This is me at the base of a radio frequency telescope, if you will. So this is listening for signals from space. And if you compare it to the one on the right, this is a tiny telescope in comparison. So this is what we use to receive light from space. So you can see the one on the left, you can't just pick up and put in a car and take wherever you need to go to actually talk to space. So it's a really cool demonstration that we were able to pull off. Yeah. And so my lab took that one step further, and I have a cool video to show you on the next slide. It's really quick. It's just like a little animation. But instead of just talking from space to ground with lasers, we decided we were going to talk from one satellite to another satellite in space with lasers. So this is really cool. If you have one satellite that sees something on the ground and it needs to tell its neighbor, you're able to kind of point at your neighbor and speak to it really quickly with lasers in space. And so we designed these two, this mission called CLICK, which is the CubeSat laser communication. So again, that payload, the communications payload, cross-link because they're talking across to each other, and then demonstration. So this was another technology demonstration. And in space, it looks like this. So if you can see this movie, when you have the two satellites kind of separating and talking to each other, this is what it would look like in space. And I forgot to loop it, so I'll just show you this really quick. Yeah, do y'all have any questions so far? I have a few more examples. Not yet? Okay. Another mission that we built in my lab was called AeroVista. Do you all know do you see the background on the slide? Do you all know what that is? Have you seen this before? Anybody? Nope. So if you see, it's kind of hard to see. Maybe I can exit out and kind of show you. I'll just like pull these things away really quick. But it is actually the sky is glowing. Have you all heard of that before, where the sky glows when it's really dark? Yeah, Ryan, do you know what it's called?
It was called the Northern Lights.
Yes, perfect. So it's actually the Northern Lights, and it also happens at the South Pole. So we have the Northern Lights and the Southern Lights. And another word for this is the aurora. So my lab actually developed two twin CubeSats. So I'm going to make my screen big again so you can see. So these are shoebox-sized satellites called Arrow and Vista, and they are sisters. So they're built exactly the same. They can do the exact same thing, and they go into space and study the aurora. So the aurora actually tells us, in looking at it in the way that we are, it tells us how the sun is behaving in terms of the way that it's interacting with the earth. So the sun likes to throw particles at us. Sometimes they're really fast and really high energy, and the earth kind of shields us from that. And we want to be able to understand how exactly it's shielding us from that, and kind of what's happening there. We know that it's doing a really good job, because it protects us. And when it's actively protecting us, that's when we see the aurora that you see on the slide. So those are other examples. The last example I'm going to talk about is actually my dissertation. So this is a bunch of fancy words. So I'm going to skip past this slide and just briefly, I'll explain this to you in other words. So what I did for my PhD is I took cameras and 6U satellites. So again, that's the size of a shoebox. And I was like, okay, if we put those cameras in space and we look down at the ocean, how well can we see the ocean from space? And what data can we get to learn about the science that's happening in the ocean? So Ryan, I think it was you who said you were interested in Saturn, right? Yeah, so Saturn is really cool. It's made of a bunch of rock and ice. And so people are really interested in knowing what the rings of Saturn are made of and what the gas on Saturn's surface is kind of made of and what it's doing. And the types of cameras that I use, if you were to point them at Saturn, you can actually see all of that stuff happening in the camera. And so those cameras, they're very fancy and they're called hyperspectral imagers. It's like a little bit of a tongue twister. But all that means is that exactly what I said, when you point at something, you can see all of the parts of it. So this is a little bit too many words happening. But the takeaway is that every material that exists, your hair, your shirt, your couch, the grass, rocks, water, every single material that exists has a unique thumbprint if you know how to look at it. So everything either absorbs light, which means it sucks it all in and you can't see it anymore, or it reflects light, which means light bounces off of it in different types of ways. And every single material, your cat, your dog, an elephant, everything reflects light and absorbs light in a different way. And so if you take these hyperspectral imagers, you can point them at something like your living room, your backyard, a forest, and you can tell at all the different types of things that are in the picture. So you can see the different types of trees, you can see the different types of soil, maybe even different types of birds, if there are like a lot of them, with these really fancy cameras. And for my work, only 2 cameras had ever flown on these CubeSats that have been dedicated to studying the ocean to try to figure out what's happening in the ocean. And so a question that I get a lot is, why would I look at the ocean? Like, why would I look at the color of the ocean? So if you saw this picture, would you know that this is actually our ocean from space? What do you think it looks like? Wait, sorry, what did you say, Ryan?
I said it kind of looks like a clear metallic kind of slime.
It does look like slime because it's all mixed up. Have you seen the surface of Jupiter? Do you know what Jupiter looks like and how it's like all swirly and it has the big storm?
Yeah.
Yeah, whenever I look at the ocean, I think I see like Jupiter, like features from Jupiter too. Yeah. Wait, Jovita, did you have something? JD,
It,
sorry.
it kind of looked like a painting.
It does look like a painting, right? It's kind of beautiful, right? I think it's really pretty.
It
But sorry?
It is.
It is. Yeah, but this is actually our ocean from space. So you can see all the swirls is sorry. This is just water kind of swirling around. So you see these like white dots and all of these white lines that are going across the screen. You'll see those. Yeah, those are actually boats. So these are boats. The tiny white dots are boats, and the stream is from the water behind it. Over here, where it gets a little more brown, you can see some dirt kind of mixing in. And then all of the swirls that you're seeing are actually showing you how our ocean currents are moving. So they're swirling, they're ebbing, they're flowing, they're kind of mixing everything up. So this is what I looked at from space, and I wanted to know if we were to look at this, could we pull out, stuff like, oh, there's like mud over here, or there's boats over here, or there are these things that are called phytoplankton that live on the surface. That's like algae. Have you seen a pond before and it has like a layer of green stuff on top or like a little puddle of water? Yeah, so that's algae. And algae provides a lot of food for fish, and it also makes a lot of oxygen for us to breathe. So it's really important. So this is what I studied from space. I looked at algae using these satellites. And so I skipped the last slide because I'll need to end here, but I just wanted to say that that's not the only thing that you can do if you were interested in the oceans. I personally grew up like playing in the oceans, and I love to go to the beach and hang out with my family on vacation. And so the oceans were always like near and dear to my heart, and they're also, if you see this picture, most of our planet is actually covered in water. So if we want to keep track of how our planet's doing, knowing how our oceans are doing are really important. So from space, using CubeSats, you can look at these things like phytoplankton blooms that are where my mouse is on the left. Or you can also see, like on the previous slide, how the currents are behaving or how ocean fronts are actually happening, where warmer water is meeting colder water in the ocean and mixing things around. So yeah, so these are just a few examples. This is my last slide. Do you all have any questions? If you could make a CubeSat to look at something from space, what would you look at?
Let me see.
What do you think? Would you look at something on the Earth? Something outside of the Earth? Sorry?
The ash. The ash. The ash. The
My dance studio.
Nice. You can
Okay.
if you can use fancy cameras and see lots of things from space.
Yeah, I hope I see it.
Yeah. You might be able to see it on Google Maps actually. If you go to the satellite view on Google Maps, those are real images of the ground from space, from satellites.
Didn't see it. No.
Yeah.
What would you look at from space?
What would I look at?
Kai, what would you look at from space?
What would I look at?
Yeah, anything in space you want to look at or on Earth with the CubeSat?
I don't know. I guess like my church, I guess.
Okay.
You could do that.
Yeah. I actually had some friends who did mapping of different communities from space using space data. So looking at, like if my church is in this neighborhood, Like what's the temperature of the ground in this area? Like, is it hotter than over there? Like, how's the weather? You can see all different types of stuff about your community from space. So there are interesting ways to study the Earth from there for you and your community. Brian, do you have a question?
I would look at the asteroid belt.
Oh, the asteroid belt. Ooh, lots of people are looking at the asteroid belt. That'd be cool. I actually don't know if anyone's ever used a CubeSat for that before. So that could be the first. That'd be pretty
You'll be the
cool.
first, Ryan.
Yeah, that could be amazing. Asteroids are actually, they're made of all different types of stuff. So the cameras that I use might actually be useful. You could see some of them are made of dust, some of them have water, some of them have diamonds on them.
I found it from the satellite, my dance studio.
Oh yeah? Oh wait. Is it on your phone?
No, it's on my mom's phone.
Oh, that's amazing. Oh.
Yeah, I go to dance class.
Yeah, what kind of dance do you do?
I pretty much do all of them.
Nice. Oh, I love that. Wonderful. Well, unfortunately, I'm gonna have to sign off. But I really love the opportunity to chat with you all. Thank you for allowing me to come hang out with you. And if you all have any other questions, feel free to tell Naya or Keyshawn, and I will be happy to text back in and answer any of your CubeSat questions. So
Thank you so much. Can everybody say thank you, Dr. Payne?
Thank you.
Hey, Dr. Payne.
of
Thank you,
course,
Dr. Payne. We're so grateful you made
Dr.
time for
Payne.
us.
of course, of course. It's a
Thank you,
pleasure.
Dr. Payne.
Girls' models look good.
They look great. I'm like, I'm
I know,
looking, I'm
yeah.
trying to peek. All right. Well,
All
we know
right.
you have to run. We're so grateful. We will be in touch.
Sounds great. Yes. Sorry for
Okay.
for me signing on late. I'm sure the
No,
weekend was amazing. So
no,
yeah.
you were excellent. Thank you so
Yeah.
much.
All right. I'll see you all
All
later.
right.
Bye.
Okay. All right, CubeSat scientists. Let me see what you got so far. Let's see them. Ryan, excellent.
I'm waiting on my brother to come back so he can help me.
Okay, no problem. Jay, do you have your model? Oh wait, I think I saw something in the chat.
Oh no, I didn't know we were supposed to start already. I thought we was doing it together. My bad. One moment.
Oh, that's okay. That's totally fine. We got 8 minutes, or we could stay on a little longer. I don't mind. So yes, we want to start. We want to start with steps. So the instruction card is here. I don't know. Well, you should definitely have them. I made sure all of the kits were intact before I mailed them out.
No, I'm gonna just do the perforated edges for you, and you can do the rest.
Let me do
Because
this.
we only got 2 minutes left.
Right. No, that's perfect. And so, did you finish, Ryan? Do you have all your subsystems in yet?
Almost.
Almost? Okay, nice. But you got your housing. Okay. And Kai, looks like you were perforating your edges. That sounds funny. Okay.
Don't.
Excellent.
It's tearing.
Okay, so while we continue, we talked about the future. So, all right, in the meantime, I would also like you all, because at 7:03, we're going to talk about our CubeSat missions. So you're all doctors at NASA. Well, you're all PhD scientists at NASA, and you're building your own CubeSat. And I want to know what your CubeSat is going to do. So start thinking about it. And we'll talk about it when we are for the end of the session.
For you, that's 6:03. That's in 10 minutes.
Oh, I'm sorry. That's right. Forget, we got time zone differences.
Mm-hmm.
Okay. So yes, it should look like this. And I will say, just take care with perforating those edges. You can rip certain things. It isn't the end of the world, but you just have a nicer product when you take your time. You could also just cut along the edges as opposed to taking them off through the perforation. Um,
Mm-hmm. You want to do this one?
Yes.
nice. What subsystem are you putting in first, Ryan? Okay. The payload? Okay. So as you're thinking about your missions, I would like you to think about, depending on what you're going to do, think about what that payload should probably be. Because payload is just a general term. Your payload could be anything, but it's going to be relevant to your mission and what you want to research or what you want to know about. So say if I want to do what Cadence does, or sorry, Dr. Payne does, my payload would pop in where she's looking at the oceans from space. Her payload included a camera to look at those payload. I mean, sorry, to look at the ocean. Does that make sense, everybody?
Mhm.
Excellent. Nice. Y'all are doing great.
Can you
Mm-hmm.
can you explain payload again?
Yes, ma'am, I can explain payload. So we know that Dr. Payne, or actually you know, what did Dr. Payne use CubeSats to look at? She showed you the pretty picture that looked like a painting. What was she looking at there?
The
Do we
ocean.
remember? Excellent. So she used CubeSats to image or to look at the ocean. So her payload had to likely consist of a camera. So your payload will be based on your mission. So her mission was to observe and look at the Earth's oceans. So her payload had to be a camera. Say my mission is to measure the temperature in Jupiter's atmosphere somehow. My payload will probably consist of a thermometer or a temperature gauge of some kind. Does that make sense?
Yes.
Nice. All right. And this is what I want you to think about for your own missions. What you want to learn, what do you think you'll need to learn what you want to learn? And once you have those edges perforated, it's very, very simple. It's just folding it like origami kind of, but don't fold too hard because you want to make sure you're folding in the right places. But we'll kind of bend it to the pre-bent or the pre-lined creases in the kit. And then it should just fold on top of itself to make a cube. So the perforation is the hardest part. And make sure you do not rip up your antenna. This yellow ruler is your antenna. We're gonna need that. Okay. Ooh. Nice. How many of you like Dr. Payne's presentation? Nice. And what was your favorite part? Anybody got a favorite?
When she showed us pictures, when she showed us pictures of photos she took of the of the ocean.
Nice. I thought that was really cool too. And what I love about her research, it is very, very necessary what she does because she's interested in helping us mitigate or fix climate change, or helping us understand it better so that we can create solutions to fix it. And that's really, really impactful work because climate change is a very real thing. And she's getting to use space technology to address those kinds of things. And I think that's really, really neat. And it shows how versatile space is and how versatile space technology is. Great job, right? That looks great.
So
Great job. All right. 7:01. Y'all got 2 minutes to think about these space missions. Dr. Rye, Dr. Kai, and Dr. Jade. Even if you're not finished, you can always finish this one on your own time too. But I do want to hear about these missions.
okay, this one. Write it.
Okay, so once you start loading your payloads, I think, Ryan, you're about there. Okay, looks like you got it. I was just gonna say, you may want to do 2 and then just stack 2 of them, then slide your antenna through the slots that you make. And then you will want to put your electrical power system on top of that, because that one's designated to go on top of the antenna.
What about the oh yeah, we gotta close it.
Like this.
I'm almost finished.
I see. Looks excellent.
We're almost finished too. No, actually, we're finished.
Let me see. Let me see, Jade.
I'm finished.
I mean, Dr. Jade, you gotta correct me. You guys are PhD scientists. You say, put some respect on my name. Don't let me call you anything other than doctor.
Here's mine.
Excellent. Beautiful job. I'm so excited to hear about what it's going to do and what science it's going to teach us about. Good job, Dr. Ryan.
Thank you. I'm still trying to think of the stuff I'm gonna bring, but I still know where I'm gonna go and look at.
Good. Good. Because we can all help you now. We can all brainstorm a good payload to learn about what you want to learn about. That looks good, Kai. Dr. Kai. You're getting there. You just got to get those edges off. All right, let's see. It's 7:04, so we're actually over schedule. We're acting a lot like we're in actual industry, actually. So I'm gonna start. It's okay if you're not finished. It's totally fine. You'll have plenty of time to do it. But I do want to hear about these missions. So I'm gonna start with Dr. Ryan, if you're ready. I want to hear about where you're going, what you want to learn, and what you're gonna take to learn what you want to learn.
I want to go to that asteroid field. I will probably take a camera so I can take pictures so I can study about it. And then I'm probably gonna send this with some different materials. Maybe I might use a magnifying glass, maybe.
Good job.
I might use like a little, I might see if I could use this to collect some rocks from space so I could study them and bring them back.
Excellent. That's great job, Dr. Ryan.
Thank you.
Okay, so is her name McKenna?
Yeah.
Okay, McKenna's your astronaut. She's on the space station. She's gonna launch your astronaut from this. I mean, she's gonna launch your CubeSat from the space station so it can go to that asteroid. It'll need some propulsion too. Can't just use the strength of the astronaut's hand. But we got a really great start.
Thanks.
Good job. Good job, Dr. Ryan. Okay, Dr. Jade, are you ready to tell me about your mission? So where you want to go, what you want to learn, and what tools you will put in your CubeSat to learn about those things.
So my mission is to see a mountain, and then
Huh?
what else did I do?
Girl, you said you wanted to learn about the mountain. You was gonna have your satellite over a mountain,
Yes.
so you can help mountain climbers.
To
Oh,
make them,
wow.
because sometimes
I'm sorry.
they die. Sometimes they die, so I would like help them stay alive.
That's good.
That is so good. Dr. Jade, you are saving lives, girl. That's so good. So
Thank
great.
you.
So you're so welcome. And so whenever we want to image the Earth, we actually send our CubeSats or satellites, spacecraft into something called LEO. Anybody know what LEO means? LEO?
No, I don't.
Okay. It's Ryan.
I said I heard of it, but I don't know what it is.
That's okay. That's you know what? We should all complain. The space industry uses too many acronyms. We'll start a petition. But LEO, LEO stands for low Earth orbit. So actually, let me pull up what altitude that is. LEO altitude. So that is only 1,200 miles above the Earth. And it's very convenient for observation. So that's where that's the orbit, the low Earth orbit that Dr. Jade's CubeSat will go in to look at these mountains and help those mountain climbers. So how amazing is that? All right, Dr. Kai. I know you're still building because, I mean, it takes time to make greatness. But I would love to know what mission you have. So where are you going? What do you want to learn about where you're going? And how are you going to learn those things? What tools do you need?
I also kind of wanted to do like a little asteroid thing also.
Good. That's good.
And I want to learn like why or how they built asteroids.
Yes.
And yeah.
That's excellent. So you want to learn about asteroid formation, and that can tell you so much. As a matter of fact, we have a resident astrophysicist on the call right now, Dr. Keyshawn.
Almost.
What can we listen? We're living right now, okay? We're manifesting. Dr. Keyshawn, what can we learn about, I guess, planetary formation based off looking at asteroid formation?
Mm-hmm. So, Kai, that's a good one. Asteroid formation is a good question because, well, so when you think about the asteroid belt, you kind of have to think about the solar system as a whole. So the way that the entire solar system formed is that way back when the sun, so our star, when the sun formed, it basically a bunch of gas and material collapsed until it was hot enough in the center for the sun to start shining. And so you had all this other material in like a disk kind of outside, and the whole thing would spin because when something starts moving, it doesn't stop unless there's something to stop it. So whole disk is spinning, and then within the disk, you get little clumps of material that start to gather up, and they start to make the planets. You get Mercury, Venus, Earth, Mars. Then you have the asteroid belt, which is a bunch of little clumps of rock that don't quite make it to be whole planets, just kind of chunked up little bits of rock. And then after that, you get into Jupiter and Saturn and the gassy planets beyond that, where it's colder and they're not made of rock, they're not solid. So asteroid formation really tells you more about solar system formation, planet formation as a whole, and that ties into stars and stellar evolution and the kind of astrophysics that me and my friends work on is really related to a lot of very big questions. So Kai, that's a good question about how asteroids get there.
Look at that. You are about to discover how we got here, why, when, who, what, where, why, how, and all that good stuff. That's incredible. You all have done an amazing job, and I'm so honored to have built some CubeSats with the finest minds at NASA or whatever space whatever space company you adore the most. I would like for us to take a quick photo, if I can manage. I have too many screens open. A quick photo with our CubeSats or almost CubeSats, even if you hold up a either kid or what do you call it, one of the subsystems, so we can get a cute photo. And I'm gonna pray I can do this properly. What is this? This is a snip. Oh, I can record? That's fly. Well, I guess we are recording right now. I'll just do a picture. Okay. Let me know when y'all are ready. Good job. I love it. All right, everybody got it up? 1, 2, 3. All right. Beautiful. We're gonna take one more. Make a silly face. Wait, give me 1 second before you start making that face. You're gonna be mad at me. Let me see. All right, let me save that. All right, we're gonna do one more. Oh, wait, I want to do a really cute face, but I can't. Okay, maybe I do this. 1, 2, 3. Beautiful. All right. Well, thank you so much. I have had a blast. I hope you have had a blast building your own CubeSats and mapping out your missions and thinking about the mission design of a CubeSat. You are literally brilliant. I wish I could do these things at your age. You're way ahead of the curve, and I'm just so excited. Does anybody like CubeSats a lot after this workshop?
I do.
You don't? You do? Okay. I was gonna say that's so
I
real.
don't either. I don't either.
You know, she is out from them. She out.
That's okay. You want to know why that's okay, Dr. Jade? Because the whole point of doing these types of things, even when you get to be in college and you do internships, you do these things and you learn about them because you want to know what you do and don't like. So when you get in your career, you're not stuck somewhere you don't like, building CubeSats that you don't want to make. So that's totally valid. That's the whole point. I love it. But no, I've had a really great time. Does anybody have any parting messages.
Me too.
So I'm gonna go ahead and wrap us up soon.
So hurry up.
I know
Any
you
last
keep it track,
questions?
but if you finish your build and you send me a picture, I'll send Naya the picture if you finish building your CubeSat.
Yes. Yes, I would like to see it. And you can customize it too. You could put some Legos in there, some Barbie dolls, you know. You just have to explain why. I just want to know why. But I'm very, very proud of you all. You all are so brilliant. You answered the questions flawlessly. You listened very, very well. And I hope that you will continue to stay connected to the Black and Astro organization, because we want to do a lot more engagement with you all. And we'd also like to hear what you want to learn about, because we just learned CubeSats may not be all that. So what do you want to learn about, so that we can create some content and workshops to teach you about it? Does that sound good? Does that sound good? Did we at least have fun? Did we learn? Good job, Jade. Dr. Jade, excuse me. That looks beautiful. Okay. Good job. So you all got 1 new CubeSats. Excuse me. Well, thank you. I'm gonna go ahead and close this out. Keyshawn, did you have any last things? Are we all good?
Yeah, I was just say thanks everybody for coming. I hope you had fun. And like Naya
Yes.
said, we're gonna do more Black and Astro programming with kids in the future on different topics. This was aerospace. We could do something astronomy in the future. Just stay
Yes.
connected, and we'll be in touch.
Okay. And I would be remiss if I didn't say this. Thank you, Dr. Parents. Y'all make the world go round. We thank you for getting your babies. I know you're probably tired after work, so we're gonna let you go. But thank you.
Thank you. This was
Yes.
fun and educational. Thank you.
Thank you,
I'm
Katie,
so
for helping
glad you
Kai.
enjoyed. Yes. Thank you, Dr. Parents and siblings and whoever else.
Yeah.
All right, we're gonna go ahead and end it. You all, I'll make sure you have my information if you have any more questions, but we will see you at the next event.
Bye, y'all.
Thank you,
Bye.
Bye.
Of course. Bye, Ryan.
Bye. Click leave. I want to learn.
Jesus.